Hey,
Can you hear me, Hunter?
yeah, I can hear you.
Okay, how's it going?
Pretty good. Going all right.
Good. I'm just trying to put my second ear in. Uh, it's pretty disturbing this morning. I saw the Today Show did a story on college students cheating. Pretty
Yeah.
depressing. Pretty depressing.
My, what did it say?
Basically, it said that students were using things like there was one site, Chug or something like that, that
Yeah.
that they were accessing. In other words, homework, instead of trying to do it yourself, you were just going online and cutting and pasting the answer. It was pretty
No,
disturbing. But what are you going to do, Hunter?
I don't know. I don't think it's going to be much of an issue because I'm pretty sure those things cost like money. You know what I mean?
I'm sure they do. And
College students are broke as hell.
uh, that's true. Yes and no. I mean, when you get to the more elite universities, what's that your what's
That's
that
a
your
good point.
what's your shirt say? What does your shirt
So
say?
it says warning,
Ah,
continue at own risk. This site may be
harmful.
harmful
Harm,
to your computer.
um, in any case, how are you doing with this stuff? You doing okay with it? Does it make sense to
The
you?
homework is nuts. I didn't do good on the homework at all. I actually got a 55 on the homework. So I really need to step up my game with it.
Ask questions, Hunter.
Yeah.
I mean, and you do have more than one attempt at this stuff.
Well, on the homework, it's once you go through it, you have to. They say you can review it, but I'm pretty sure you can't. Like, there's no extra attempts at the homework.
Yeah, I think there are.
Are you sure?
I'm pretty sure there are.
Oh,
Maybe not once you finally submit it, but
yeah.
up till that point, I'm sure you have. What the hell was that thing?
It's a neck massager. You know what I mean?
Okay.
Because I'm sitting. I mean, I sit and I do work all day. You know what I mean? I gotta have a neck massager sometimes.
Hey, everything, everything has a cost. Do you know what kind of problems you were having trouble with, Hunter?
Let me go back to the homework. Pretty much like all of it, but I just gotta do more repetition with it. Let me see. See. I'm going to the Pearson now.
Do I need to get in there?
No, it's okay. I'm just gonna tell you what the
What the problem basically is?
yeah.
Hey, Zaina.
For some reason, it won't let me. Okay, never mind. Hold on. Homework 7 empirical formula. Okay, the first part I bombed it,
Are
and
you
the
talking
first
about
part was
the iron
the
compounds?
because
Was it the
yeah, I
iron?
think so.
Oh, those are all mass
Yeah,
percents.
yeah, yeah. It was.
All you got to do, Hunter, is take find the mass percent of iron in those compounds, and then take that percentage and apply it to the total weight.
But when I tried to put it in, for some reason, I don't know, it like wouldn't mark it, and then it came up with like another answer. Like, I don't know, it was weird.
Uh, I don't know what. Give me one of the problems there.
All right, so you're gonna have to, you would have to open it up. But iron is found in the Earth's crust and has several iron compounds. Calculate the mass in kilograms of each compound that contains 3.6 to 10 to the third kilograms of iron.
Okay.
And then part A was going to be iron subscript 2 and then oxygen subscript 3, which is hematite.
Okay, or rust. Or rust.
Oh, really?
Yeah. Okay. So the first thing you're going to do here is you're going to.
Let me get my chemistry file out. Hold on.
Zaina, how you doing?
Okay, I have my notes out now. Okay, so you said the first thing?
All right, you got 2 irons and 3 oxygens, right?
Yeah.
All right, so iron's atomic weight is 55.85. Check to make sure that I'm right on that. I don't have a periodic table with me.
I do. I have it right here. 55.845.
Okay, close enough.
Yeah.
All right, so I have 2 of them, so that means I have 111.70. Right?
Yeah.
So to the 111.70, I had 3 oxygens, which are 48.
I thought oxygen is 15.999.
It's close enough to 16, Hunter.
Okay.
So
Yeah,
I add
48.
the 48 to the 111.70, I get 159.70. Then I take 111.70 and divide it by 159.70. And this gives me basically 70%, 69.94.
Yeah.
All right. So 69.94% of 3.6 times 10 to the third kilograms is going to be my answer.
69% times, say that one more time.
69.94% of 3.6 times 10 to the third kilograms is going to be your answer then.
Well, the answer on the homework is mass equal 5.2 times 10 to the third kilograms. So maybe it's jacked up on the website. I mean, I'm Pearson.
Did they give you any hints? I may be doing something wrong. Hi, Victoria.
No, I didn't use any, or I didn't use the hint.
Hi.
Hi, Victoria.
I'm making pasta. I'll be back. Bye.
Hi.
She said pasta.
Yeah, apparently she's cooking dinner. Oh, we're at 5:30.
I have dinner on the way to me.
Hunter, that's how I would do it. I'll look into it.
Yeah.
I'll look
Okay.
into it. And if I see something different after I look into it with the homework, I'll email you. If I don't email you, that means that everything is basically the same. Okay.
Okay, I appreciate it. Because
And
that first part was definitely a little funky.
I don't see what could be different. I don't see what I did was wrong.
Yeah, it's all good.
Wait, that's not possible. They said 5,200.
They recorded the answer as it says, okay, the question, iron is found in the Earth's crust as several iron compounds. Calculate the mass of each compound that contains 3.6 times 10 to the third kg of iron. And then the part A, which is question 1, Fe2, and then oxygen 3 hematite, the answer is recorded as 5.2 times 10 to the third
That's not
kilogram.
possible. That's not possible.
That's what I'm saying. That's why I was like sitting in the homework like, what in the hell? And the first part of the exercise of the homework is worth the most. So if it's all messed up on the first part, then it's going to throw off the whole homework.
Wait, is it the first question? Because I was like,
Homework 7, yeah.
yeah, we did like the steps, and I followed the steps, and it was like in scientific notation. I was like, I thought they wanted.
No, it's not. Well, wait, guys, it's not possible, because if you start off with 3.6, 10 to the third, maybe it's the other way around. Let's do it that way. Maybe I misunderstood the question.
I want to go back to my pasta.
That's the question. That's the problem. All right. It's not okay. The question, Hunter, is I'm sorry, I misunderstood the question. All right. The question is, how much hematite would you have to mine to get 3.6 10 to the third kilograms of iron?
Oh.
All right. So it's 69.94. That part was correct. But it's you don't know what the total is. You don't know what the hematite weight is. But what you do know is the weight of iron. So it's 69.94% of X equals 3.6 10 to the third kilograms of iron. You understand? Okay, you understanding, Hunter?
A little bit.
Okay, anybody else have any questions? I'm only got 10 people here tonight. What's going on here, guys?
It'll probably fill up in the last 5 minutes before class.
Well, they'll try and get the get it on there. Okay. Hard question. This is probably the hardest question I have in my repertoire today. Upon combustion, 0.8233 grams sample of a compound containing only carbon, hydrogen, and oxygen produces 2.445 grams of CO2 and 0.6003 grams of water. What is the empirical formula of the compound? Remember, guys, what's the first step to doing empirical formula problems? What do we have to find? First thing.
The weight of each element.
We have to find the weights of each element, okay? Well, first off, we have carbon dioxide and we have water. In the other problem like this, what did we do? Do you remember what we did?
We multiplied the subscripts times the atomic weight.
I'm not understanding. Okay. You're saying you get the molecular weight. Is that what you're saying, Hunter?
Yeah.
Okay. You get the molecular weight. How do we get the weight of carbon?
Periodic table.
That's how you get the atomic weight. How do we get the actual weight of carbon? All right. Go ahead.
Don't you multiply the I don't know if I'm saying this correctly.
Percent.
The percentage of what the carbon would be in the total molecular weight times that weight that it's giving you to find the carbon.
Exactly. Great. Who's talking?
Jennifer.
Jennifer, good job.
Sorry, I was still making my pasta, but I can still hear.
What Jennifer is saying is you find the mass percent of carbon in carbon dioxide and you just simply multiply that percentage by the 2.445. That gets you the weight of the carbon. All right, similarly, how are we going to get the weight of our hydrogen?
You're going to do the same thing. You have to set them up for all of them.
Ah, there's a trick here. So yes, in order to get my carbon, I'm going to take my 12 grams of carbon, divide it by the weight of carbon dioxide. That percentage is about 27.3. I'm going to multiply that by, I don't know where that came from. This should be 2.445. Okay, I do that math out. That gives me 0.667. Okay. I do the same thing for my hydrogen. There are 2 grams of hydrogen in 18. That gives me about 11.1. And my hydrogen weighs 0.6003. This gives me 0.0667. All right. Now remember, my original problem said my original compound had carbon, hydrogen, and oxygen in there. I know what my compound weighed. I also know how much carbon I have in there and how much hydrogen I have in there. How am I going to get the weight of the oxygen? Come on.
Subtract.
Very good, Kaylin. Very good. Now, what you may think, guys, you may think, oh, I got the percentage of carbon by taking the 12 grams of carbon and dividing it by the CO2. So shouldn't I be able to get the oxygen by taking 32 and divide it by 44, right? You may think that. The trouble is, remember what happens in combustion. We're taking our compound, CHO, plus O2, and we're reacting it, right? So when we do that, are we not adding extra oxygen into it? The oxygen that is created and makes CO2, part of it comes from O2 and not the compound we're targeting. So therefore, you can't do what we're doing up top. What we have to do is what we have to do is we have to take the total weight of our compound, subtract the weight of our carbon from it, and then subtract the weight of our hydrogen. What is left is going to be the weight of our oxygen. So my 0.8233, which was the weight of my whole compound, minus the weight of my carbon, minus the weight of my carbon, oxygen, this gives me 0.888 grams of oxygen. I have my 3 compounds now, my 3 compound weights. Next step, guys, once we have the weights, We have the weights of all three things now. What do we do next in an empirical formula problem?
Get the moles of the weight.
Get the moles.
Or
So I'm
turn
going
them
to
into
take
moles.
my weight of carbon, divide it by 12. This gives me 0.05556. My weight of hydrogen divided by 1.008. This gives me 0.0664 moles of hydrogen. My weight of oxygen divided by 16, 0.00555. Now I've got all the weights. What do I do then?
Divide it by the smallest mole.
Divide it by the smallest mole, which is the oxygen. I divide it into oxygen, I get 1. I divide it into the moles of hydrogen, I get 12. Moles of carbon into the moles of carbon, I get 10. So my empirical weight is C10H12O. Guys, you got to remember that. The steps, find the weights. Second step, turn the weights into moles. Third step, divide by the smallest number of moles. Fourth step, if necessary, use an integer. That was the hardest problem you'll probably have to deal with. All right, ladies and gentlemen, let's think about this one. How much, in terms of kilograms, K2O could be produced from 500 grams of potassium? All right. What's the ratio of moles of potassium to moles in the potassium oxide? Come on, guys. What's the ratio? Potassium. What's the subscript on potassium?
Would it be 2:1?
2:1. I have 2 moles in the potassium oxide for every 1 mole of the potassium. So the ratio between them is 1:2, right? Right? So what I'm going to do, I have my grams of potassium. All I have to do is take my kilograms of potassium, change that into grams. Then I'm going to change my grams of potassium into moles of potassium. Then I know that I have 1 mole of K2O to every 2 moles of K. So I'm going to take my moles of potassium and multiply it by 1/2. This gives me 6.93 e to the 3rd moles of K2O. In order to find the grams of the K2O, all I got to do then is multiply by the molecular weight. This gives me 6.02 e to the 5th grams, or 602 kilograms of potassium oxide. Did you see the logic behind that, ladies and gentlemen? You have just done your first stoichiometry problem. And that's where we're going from here. Stoichiometry. What we're doing in stoichiometry is we are determining how much of one reactant we need to react with another reactant. We're going to need to find out how much product can be made from one reactant. We're going to be able to determine, if I know how much product I made, how much reactant it took to make that much product. And if I know how much product I made, how much byproduct was done with it. All we are doing is we're doing chemical recipes. We're finding out how much of one substance we have, and we're converting that into how much of another substance we need. All right, first of all, just a little bit of review. The balanced chemical equation is going to be used to determine the relationship between moles of reactants and moles of products. Okay, we're going to learn to do that today. We're going to learn to understand what the limiting reagent is, and we're going to use the limiting reagent to do stoichiometric calculations. Guys, these are a lot easier than empirical formula problems because it goes by a straightforward strategy. Then after we do that, we're going to determine actual yields as a percent of theoretical yield.
Mr. Popovich,
Yep.
sorry to disrupt you, but some people are trying to join the Zoom. They got kicked out.
Sorry. Thank you so much.
You're welcome.
They should be in now. I just pulled about 10 people. Sorry, I wasn't paying attention. I was going on with the lecture and not paying attention to that. Okay, guys. It doesn't matter. They just, the first of what I did this was just a review of what I've been doing. Okay, so if we get a color change from what the reactants look like, it's probably that we have a chemical reaction. If you get a solid forming, bubbles forming, if you get a heat or if a flame is produced, or sometimes if you get heat absorbed. These are all examples of a chemical reaction taking place. Now, when we're involving in chemical reactions, what you have to understand is we're rearranging the atoms. But in the rearrangement of these atoms, we have to realize that because of the conservation of mass, we don't create or destroy atoms. All the atoms that are present in the reactants must be present on the product side. This is what we were doing when we were balancing the chemical reactions. We also have to realize that we're dealing with physical states as well. Again, this is nothing more than review of things that we've had already. So, in order to do stoichiometry, we have to deal with two things we've had before. The first is the concept of moles. Second is balancing chemical equations. Now, when we're dealing with balanced chemical equations, what that does is that shows the relationship between the relative numbers of reacting molecules and the product molecules. So if I have carbon monoxide reacting with oxygen, what I actually am doing when I'm reading this chemical equation is I should be thinking 2 carbon monoxide molecules react with 1 oxygen molecule to produce 2 carbon dioxide molecules. Or if I want to up this to moles, every time, at least silently, guys, when you're looking at a chemical equation, you should be thinking to yourself, the coefficient stands for the number of moles of that particular compound. And in this case, if I'm dealing with the molar level, 2 moles of carbon monoxide react with 1 mole of oxygen to make 2 moles of carbon dioxide. All we're doing is we're just doing chemical recipes. So, ladies and gentlemen, if I'm going to make my recipe, I go to my pantry, I pull out 4 cups of flour, I grab 3 cups of apples, I pull out 1 cup of sugar, and I throw in 1/10 of a cup of spices. And what I end up with is 14 fats. Fantastic apple tarts. Now, when I'm thinking about this, in order to make 14 fantastic apple tarts, I need 4 cups of flour, 3 cups of apples, 1 cup of sugar, and 1/10 cup of spices. If I don't have that much, I can't make my 14 apple tarts. I need each one of those ingredients. Same thing happens when we're dealing with chemicals. If I'm going to make 28, I'm going to need more stuff. I'm going to need 8 cups of flour, 6 cups of apples, 2 cups of sugar, and 0.2 cups of spices. In chemistry, though, when we're doing these recipes, instead of using cups, we're going to use moles. So when I get my recipe for making carbon dioxide, I need 2 moles of carbon monoxide with 1 mole of oxygen, and that will make me 2 moles of carbon dioxide. Is this kind of making sense, guys? Do you notice I am not saying grams? I am not saying grams. I am saying moles. Because there's a relationship of moles of carbon monoxide to moles of oxygen. And that relationship is 2 moles of carbon monoxide to 1 mole of oxygen. I haven't entered into grams. We cannot use grams. 2 grams of carbon monoxide and 1 gram of oxygen will not give you 2 grams of carbon dioxide. It defies the law of conservation of mass. So we cannot use grams. We have to do this by an indirect method. We have to go through moles. Remember, when we were talking empirical formulas, the subscript stood for the molar ratio of atoms within that compound. So if I'm dealing with calcium phosphate, the molar ratio is 3 moles calcium to 2 moles phosphorus to 8 moles oxygen. If I'm looking at a chemical reaction, for this reaction to proceed in its entirety, I'm going to need 2 moles of sodium phosphate, 3 moles of calcium chloride. If I have that, what will happen is I'm going to make 6 moles of sodium chloride and 1 mole of calcium phosphate. Maria, as bored as you are, Maria, does this make sense to you? Come on, Maria.
Kind of.
Kind of? We're going to work some problems out. So when I'm dealing with a chemical reaction, I've got A of A plus B of B yielding C of C and D of D. If I start off with an amount of A, I can't directly go from grams of A to grams of C. I can't do it. I have to go by a different route. Think of it like this. If you're traveling from here to Tampa and the Howard Franklin Bridge has had a nuclear bomb put on it, there's no more Howard Franklin Bridge. I can't go that way. So I either have to go through the Courtney Campbell or through the Gandhi. I can't go directly. I have to go through another route. The other route we use are moles. I don't have a relationship, grams of A to grams of C, but I do have a relationship, moles of A to moles of C. So I have to first take my mass of A, turn it into moles of A, Then, since I know the relationship, moles of A to moles of C, I can turn it into moles of C. Then I can turn it back into grams of C. So I can't go directly. I have to go by a circuitous route. Solving problems. Read the problem. Find out what you want to know and what you have that's given. Make sure that your equation is balanced. Make sure your chemicals in the equation are balanced, and make sure the chemical equation itself is balanced. Write down the given masses of the reactant or product, everything that you know. Determine the number of moles using the molecular weights. If you've got grams, you have to turn that into moles by multiplying by 1 mole over the molecular weight. The other tool you have at hand here, if you have liters of a gas at STP, then you know that 1 mole over 22.414 liters will get you to moles. Now, the next thing you do, you look at your balanced chemical equation and you look at the coefficients. The coefficients are the molar ratio. In my equation, 2 moles of sodium phosphate will make 6 moles of sodium chloride. My molar ratio between sodium phosphate and sodium chloride is for every 2 moles of this I have, I make 6 moles of that. So if I've got moles of sodium phosphate, I multiply it by 6 moles of sodium chloride over 2 moles of sodium phosphate. Last step, once I have moles of my unknown, I multiply it by its molecular weight over 1 mole. So bottom line, I know I have it in 6 steps here, but there's some extraneous things here. Bottom line, find your known. If you have grams of your known, first step, turn your grams of known into moles of known by dividing by the molecular weight. Second step, use the ratio of the coefficients in the balanced chemical equation to change from your moles of known into moles of unknown. Then once you have your moles of unknown, multiply it by the molecular weight of your unknown over 1 mole. This will give you the grams of your unknown. Ladies and gentlemen, each and every one of the problems we're going to do today and Thursday, each one of them will involve those 3 steps. Got a whole bunch of problems here. Okay? Sorry. How many moles of phosphoric acid are required to react with 2.5 moles of water? I'm sorry, excuse me. How many moles of phosphoric acid are required to form 2.50 moles of water? Do I already know how many moles of my product I'm making?
Yes.
If I already know how many moles of the product I'm making, then I don't have to convert it into moles, do I? Come on. Don't be shy.
No.
No. Save yourself a step. The first problem up there has given us the answer in moles. So in that first problem, what we know is that we have 2.5 moles of H2O. Do we know the relationship between moles of phosphoric acid and moles of water? Kaylin,
Yes.
what is that relationship?
Moles of phosphoric acid to water,
Yes,
2 to 3.
2 to 3. So I know that for every 2 moles of phosphoric acid I consume, I make 3 moles of water. I already know how much water I made. So from the equation, I know that my ratio is 3 to 2. And I know what my molecular formula for water is H2O and phosphoric acid. So if I know that I end up with 2.5 moles of H2O, all I have to do is use that molar ratio. I used up 2 moles of phosphoric acid to make 3 moles of water. Moles of water cancel. I end up with my moles of phosphoric acid. So I multiply 2.50 by 2 over 3. I had to have 1.67 moles of phosphoric acid to make 2.5 moles of water. I'm not done yet. I need to know how many grams. So if I have 1.67 moles of phosphoric acid, how am I going to get grams of phosphoric acid?
Can't you just go from moles to grams?
How?
Time.
Uh,
Tell me,
dimen-
Maria, I think I read your lips and you said multiply by the molar mass. Am I correct?
Yes.
yeah.
That's all you're going to have to do. You have 1.67 moles of phosphoric acid. You have the molecular weight of phosphoric acid over 1 mole. This means you ended up with 164 grams of phosphoric acid was needed to make 2.5 moles of water. Easy peasy, right, guys?
Is it just basically dimensional analysis?
Basically, straight up, Victoria.
Got it.
These things, these particular problems are not that difficult. How many grams of sodium phosphate would be formed if 1.75 moles of H3PO4 were consumed? I don't know if this is the next problem or not. Let me try and just go straight through. I was trying to do something cute here. Yeah, it is the next problem. All right, guys. Do I need to change from grams to moles of the phosphoric acid?
No.
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 Nope. Okay. Now, moles of phosphoric acid are given. What's the relationship between phosphoric acid and sodium phosphate?
2, 2.
2,
Is it
2.
1 to 1?
1 to 1. So if I had 1.75 moles of phosphoric acid, how much sodium phosphate did I make? Curtis, you just said it was a 1-to-1 relationship.
1.75.
Thank you. Sometimes the easiest answer is the best answer. Nope. I don't know what I'm doing here. So if we started with 1.75, the molar ratio is 2 to 2. We end up with 1.75 moles of sodium phosphate. Now, Curtis, how are we going to get grams of sodium phosphate?
We multiply it by the atomic weight of
Molecular weight.
molecular weight.
Molecular weight, but you're right. So all I got to do is figure out what sodium phosphate weighs. And guys, I'm not going to go and recalculate these molecular weights. I'm going to assume you all know how to calculate a molecular weight at this point. So all I'm going to do here is take my moles of sodium phosphate, multiply it by my molecular weight over 1 mole. This gives me the amount of grams of sodium phosphate I can make from 1.75 moles of phosphoric acid. Questions?
Just a quick question, I'm sorry. The 163.94 was the molecular weight?
Yes, I believe so, Mila. Let me go. I'm trying to go back. Yes. Yes. 163.94 is the molecular weight of sodium phosphate.
Okay, thank you.
All right, new problem. I got how many grams of phosphoric acid would completely react with 162.5 grams of sodium carbonate? I don't have moles here, do I?
No.
No.
So what's the first thing I have to do?
Conversion,
Of what to what?
gram to mole,
Of grams to moles. So, and Marie, how am I going to do it?
time to 1,000.
Nope, not times 1,000.
Why don't you
How-
just do 162.5 times 1 mole over the molecular weight of
That- Exactly. Marie,
Yes,
did you see what Victoria said there?
yes, I see. Thank you.
The molecular weight of sodium carbonate is 106. So I'm going to take the 162.5, divide that by the molecular weight of sodium carbonate. This gives me 1.533 moles of sodium carbonate. Now, I want to know, though, how many grams of phosphoric acid I need to completely react that sodium carbonate. So what is the relationship I'm going to use at this point?
Grams and moles.
Nope, we've already got moles.
Molar ratio?
Oh,
Molar ratio. That Mariah?
Yeah.
All right, great, Mariah. What is the molar ratio between phosphoric acid and sodium carbonate?
2 to 3.
2 to 3. So I've got the moles of sodium carbonate. I know that I need 2 moles of phosphoric acid for every 3 moles of sodium carbonate. I do that math out. I need 1.022 moles of phosphoric acid. Next step, guys. What do I do now?
Convert it into grams.
By doing what?
Time by molar weight.
Times it. Guys, I keep asking the same questions over and over again because I want this to be robotic to you. All right. If I'm going from moles to grams, I got to multiply by the molecular weight. If I'm going from grams to moles, I got to divide by the molecular weight. I need you to have that stuff down like this so you're not even thinking of that when you're in the test. So I got my moles of phosphoric acid. I'm multiplying by grams over 1 mole. This gives me 100.1 grams of phosphoric acid. Now let's just think what we've done so far. Okay, the first problem. I had my weight of products. I had my amount of water, which is a product. I related that back to a reactant, did I not? Guys? I had my moles of water. I was able to determine how many grams of phosphoric acid. So I related a product back to a reactant. The second problem I did, I knew how much of my reactant, I knew how much my phosphoric acid I had. I determined how much sodium phosphate. So I knew how much reactant I had. I could relate that to one of my products. This problem, I'm relating one reactant to another reactant. Is it also not possible to relate one product with another product? So we can do all that, guys. The only thing we have to have is that balanced chemical equation. As long as we have the balanced chemical equation, we can relate anything within that equation to something else based upon the molar ratio. So the simple steps, we're going to find our known. We're going to turn our known into moles by multiplying it by 1 mole over the molecular weight. We're going to turn our known moles into our unknown moles using the molar ratio, which is just the coefficients in the chemical equation. Then we're going to use the moles of the unknown. We're going to multiply that by the molecular weight of the unknown over 1 mole. We get our answer. Simple 3-step process here. And this is something I've already talked about. Oh, we're producing CO2. CO2 is a gas. Can I relate phosphoric acid, which is a liquid, to how much gas I can produce?
Yes.
Can I do that? How am I going to do that?
Because it's like 22.414 liters equals 1 mole.
I can do it because of these magic 3 letters here, STP. At STP, I can relate the volume of the gas to the number of moles. So look at this strategy-wise. If I know the moles of CO2, I can tell you how many liters there are at STP, right?
Yes.
If I know the moles of phosphoric acid, I can tell you how many moles of CO2. So, Rosina, what's the first step I'm going to do in this particular problem?
Convert it into grams.
Rosina, can I relate grams of phosphoric acid to grams of CO2?
I'm totally lost today. Please
Okay.
excuse me. I'm totally lost today.
No problem, Rosina. But I can't relate grams to grams, but I can relate moles to moles. Keep that idea in your head, okay, Rosina?
Yes.
Mariah.
Yes.
If I had moles of phosphoric acid, can you tell me how many moles of CO2 I can make?
Would you have to do the molar ratio?
Absolutely. Absolutely. I'm going to take my moles of phosphoric acid and multiply it by I make 3 moles of CO2 for every 2 moles of phosphoric acid consumed. This gives me 2.63 moles of CO2. Now, throwing it out to the crowd. If I have 2.63 moles of CO2 at STP, how do I find out the volume?
Wouldn't you do 2.63 moles times 22.414 liters over 1 mole?
Wait. 2.63 moles. I'm sorry. You said that and my mind was somewhere else, Victoria. And you're going to multiply the 2.63 by?
By the 22.414 liters over 1 mole to get your volume. I don't know why I remember that number. I just do.
It's somehow certain things just stick in your mind, but you're absolutely correct. I've got my moles. Go ahead.
I'm sorry. How do we get that ratio 3:2? Do we just use the subscripts for CO?
No. Not the subscripts, Curtis, the coefficients. The numbers in front of the compounds give you the molar ratio. If I have 3 moles of sodium carbonate
Mhm.
and I react with that 2 moles of phosphoric acid, I will make 2 moles of sodium phosphate, 3 moles of carbon dioxide, and 3 moles of water. That is true. Balanced chemical reactions tell you the molar ratio between all the chemicals within that chemical reaction. So that's where I'm pulling up the molar ratio from. Make sense, Curtis?
Well, so would we just add the coefficients up from the left side and the right side?
No.
I mean, not the,
You
yeah,
directly relate it. Okay, Curtis, do you see I have 1.75 moles of phosphoric acid there?
right.
If I wanted moles of CO2, all I got to do is look at the coefficient in front of the CO2, and I make 3 moles of CO2. But in order to make that, I consume 2 moles of phosphoric acid.
Gotcha.
That is the
Okay, okay.
relationship between those 2 chemicals.
Gotcha. So we take the element that we have the moles of, we put that on the bottom. And then the
Absolutely.
other element. Gotcha.
Finest kind. Absolutely tremendous.
All right.
Questions, guys? Come on, keep them coming.
Are we using the coefficient of the product or the reactant?
Both.
Okay,
Marie,
yes,
isn't phosphoric acid a reactant?
yes,
Isn't CO2 a product?
yes,
Because we have a balanced chemical reaction, I can relate any one of the chemicals to any one of the other chemicals. I could tell you right now that 1.75 moles of phosphoric acid will also make 2.3 moles of water, because the ratio between the 2, water and phosphoric acid, is also 3:2. Do you see that, Marie?
yes.
Any other questions, guys? Does this seem fairly easy?
Seems like we've been doing this for weeks now.
It seems like, what's it called? It seems like literally almost the exact same thing as what we were doing last week,
Yeah.
but just taking it from a formula.
But the difference is it's a slight nuance. You're doing basically the same calculations. The difference is you're applying it in a little bit of a different way.
Mm-hmm.
All right, let's do this in reverse. We just found out how much CO2 I could make. If I have 4.3 liters of CO2 at STP, can I find out how many grams of phosphoric acid I need to produce it? Chase.
Yes. Oh,
Sorry,
that's
Chase.
Yes, sir.
Can I turn 4.23 liters of CO2 at STP, can I turn that into moles of CO2?
You can.
By doing what?
Would you take the? You take the 4.23 and multiply it by 22.414 over 1 mole.
Either way, inverse.
Oh,
Because the way you did it, I would have liters squared over mole. When I'm doing it from liters to get the moles, I have to put 1 mole over the 22.414.
oh, okay.
That gives me 0.189 moles of CO2. Now, Chase, can I turn moles of CO2 into moles of phosphoric acid?
Yes.
What do I need to do that? How do I need to do that?
You're gonna have to find the ratio.
What is the you have all the information. What is that ratio?
I have no idea. I'm still the ratios are so confusing to me. I cannot figure it out.
Chase, this is easy.
I don't know the rate.
would it?
No,
I'm a little confused too. Would it be 3 to 3?
no.
Am I
want to know
close?
phosphoric acid. What's the
Uh,
coefficient in front of CO2?
3.
What's the coefficient in
Oh,
front?
so it'd be 2 to 3.
Correct. All right, Chase, come back to me, Chase. Spencer, I'll get to you in a second, okay? Chase,
So is it just the corresponding?
coefficients.
Oh, so it's just that easy. Okay.
Guys, I mean,
I
what
just
can I
needed to-
tell you? You're trying to make this harder than it is. All you got to do is look at the coefficients. That tells you what the molar ratio is going to be.
Professor, math is scary, okay?
Yeah. The biggest thing that trips me up is when we're doing questions like these, and then you have to add like simple things, and then sometimes they're so simple they just seem wrong.
That which is the greatest problem I
For
can
real.
give you. Do you guys remember the extra credit question?
I didn't even do it.
The extra credit question is beautiful, guys, because I said you have this many molecules of, I think, CO2. What's the density? Remember that?
Yeah, it was.
It- Yeah, it wasn't that bad at all.
All you had to do was just think a little bit. The thing that freaked you out was you were looking at this and like, oh my God, he wants to know the density. I got to find 2 values and he's only given me 1. What you did for that particular problem was you had to take the molecules, use Avogadro's number to turn that into moles. Then, since it was at STP, you got the volume by multiplying the moles by 22.414. You got the mass by multiplying by the molecular weight. Then divided the mass by the moles. The reason that question was beautiful is because it was so simple that you kind of like overthought it. And that's what's happening here. Don't overthink this. The molar ratio, the second step, all you're doing is putting whatever compound you want, the coefficient of what you want goes on top, and what you know is going to go on the bottom. Questions, guys? Come on, keep them at me. Yeah. Just to finish up this particular problem. If I get 0.189 moles of carbon dioxide, I multiply it by the coefficient 2/3, I get 0.126 moles of phosphoric acid. Now all I got to do is multiply that by the molecular weight. I get 12.3 grams of phosphoric acid. I'm tired of that equation. Let's go with another one. And let's see who I'm going to do. Brian. Brian. Brian, you there? Okay, Apple Grace, you there?
Yeah.
Okay, you have 35.6 grams of barium chloride. How much silver chloride can I make? What have we been talking about, Apple Grace? What's the first step?
Do you find the mole?
Find the moles. So I'm going to take my 35.6, multiply it by 1 mole over my molecular weight. I have 0.171 moles of barium chloride. Now, how do I turn that into moles of silver chloride? What's the ratio, Apple Grace?
2:1.
2 to 1. So for every 2 moles of silver chloride I make, I use up 1 mole of barium chloride. So I multiply that by the 0.171. This means I get 0.342 moles of silver chloride. Last step, guys. Come on, what's the last step? I have moles of silver chloride.
Converted to
Find the
grams.
molecular.
Convert it to grams by using the molecular weight. Okay? Curtis, you like ham sandwiches?
Not a big pork guy. I'm more of a turkey sandwich guy myself.
All right, so bear with me, okay, Curtis?
All right.
You're making this for your church, okay?
Okay. All right. I
You
can do
got
that.
36 slices of ham and 28 slices of bread. How many sandwiches can you make? You're generous, Curtis. You put 3 slices of ham in each sandwich.
You can make 12 ham sandwiches.
Can you?
Yeah. 3 slices of ham in each sandwich. You have 36 slices. 3 times 12 is 36.
But you have 28 slices of bread.
Oh.
Do you have enough bread to make 12 sandwiches?
No, you don't.
You don't?
You only have a.
You don't? If
No.
you're going to make 12 sandwiches, Curtis,
Oh, you need 2 pieces of bread a piece. That's 14. So you can actually make 14 with that.
no. There
Okay.
are 2 slices of bread. You're making 12 sandwiches, right?
Right.
So if you're making 12 sandwiches, how many slices of bread do you need?
24.
24.
24. Guys,
Yeah.
we're doing the same thing here. We're doing the same thing here that we did with our chemicals. If I got 3 hams and 2 breads, I make 1 sandwich, right?
Mhm.
All right. So I take my 36 slices of ham. I divide that in 3. That means I can make 12 sandwiches using the ham.
Mhm.
If I have 28 slices of bread, I'm dividing that by 2. This means I can make 14 sandwiches with the bread. But I'm going to run out of ham before I run out of bread.
Mhm.
This means my ham is limiting the amount of sandwiches I can make. Similarly, if my recipe calls for 4 cups of flour, 3 cups of apples, 1 cup of sugar, and a 1/10 cup of spices. If I go to my pantry and I can only see 2 cups of flour there, can I make 14 fantastic apple tarts?
No.
I cannot make 14. How many can I make?
7.
I can make 7 because my flour is limiting me. Because I only have 2 cups of flour, I have to cut these other things in half. So I only need 1.5 cups of apples. That means I have 1.5 cups of apples left. I only need a 1/2 cup of sugar. That means I still have a 1/2 cup of sugar left. I only need 0.05 cups of spices. That means I have 0.05 cups of spices left. I've made 7 fantastic apple tarts, but because I had these in excess, I still have some of these left. I've used up all of my flour. My flour is limiting me. In the same way, chemicals can limit the amount of product that gets formed. Does this make sense to you all?
Makes sense. That makes sense.
The
So then,
amount.
Professor,
Go ahead.
when we are doing a chemical reaction, Like in the lab, we saw that we have to use up all of the magnesium in order to find out whatever is the product. So when we are actually doing a chemical reaction and we end up not using some of the reactants, then is that okay?
Okay, Marie?
That's
Yes, it
Rosina.
is. Yes, it is. But that means when you're doing your calculation, all right, yes and no. All right. All right, Marie. In the first instance, yes, it's okay if you know how much of the limiting reagent you have, because you can use the limiting reagent to determine how much product you make. Okay? Now, Marie, if you're asking, if we go back to the empirical formula problems where you're subtracting out the weight of magnesium, is that what you're asking, Marie?
That was
Professor, it was Rosina, not Marie.
I'm sorry, Rosina. I'm sorry. Rosina, is that what you're asking?
Yeah, so what I was asking was that should we even like move forward knowing that in the chemical equation we have excess of certain chemicals? Should we still go forward when we are actually doing the chemical reaction, or should we only take the limited amount of quantity that is needed for us to get the product that we desire? Like you gave the
Marie,
example of a baking recipe. So you wouldn't necessarily use more of the other agents just because they're available. You would use only as much as what you need. So in the lab, when we are doing a chemical reaction, how does this translate?
okay, Rosina, it depends upon the question you're asked to determine. If what you are asked is how much product do you make, you're going to use the limiting reagent, and that will tell you how much product you make. Okay, Rosina, does that
Got
make
it.
sense?
Yeah, that makes sense.
Okay, now, if you remember correctly, when I was doing the empirical formula problems, I always said that the magnesium had an excess of oxygen. Okay, Marie?
Right.
I'm sorry, Rosina, I'm sorry. Okay, when I said that it had an excess of oxygen, this meant that all of the magnesium was used up.
Right.
Okay, does that make sense, Rosina?
Right. It does. Yeah.
So basically, in order for me to answer your question is a little more complicated than I think you intended it to be. It really depends upon what you're asked to solve, what you can do. Does
Got
that
it.
make sense, Rosina?
Yeah. Thank you.
Any other questions, guys? All right, now, recognition of limiting reagent problems. The way you recognize that something is a limiting reagent problem is you are given an amount of each reagent. In this particular example, I'm asked, I'm given an amount of calcium chloride, I'm given an amount of silver nitrate. And then it is asking me, how much silver chloride can I make? The question implies that I'm reacting the calcium chloride with the silver nitrate to make silver chloride. Okay? So I'm given an amount of the first reactant, I'm given an amount of the second reactant. That is how you recognize a limiting reagent problem. So what you're going to do is you are going to take the calcium chloride and you're going to find out how much silver chloride you can make from that much calcium chloride. That's going to be your first problem. Your second problem, you're going to find out how much silver chloride your silver nitrate can make. Then you are going to compare the two amounts. The reactant that made the least is going to be your limiting reagent, and the least product that was made is going to be the one that you report out, because the limiting reagent limited the amount of product you could make. Let's, guys, what time are we looking at here?
It's 6:26.
626.
Okay, we'll be able to get through this at least. So you're going to pick each reactant, and you're going to figure out how much of that one product that reactant can make. Then you're going to go to the other reactant, find out how much product that can make. And you're going to compare the two. One's going to be smaller than the other one. The one that's the smaller came from the limiting reagent. That's the one you report out. Okay, first step. If I'm given this problem, the first thing I have to do is I have to write the reaction. I've got calcium chloride, that's not balanced. I have silver nitrate making calcium nitrate and silver chloride, double replacement reaction. Next step, I have to balance each compound electronically. Calcium's a +2, chloride's a -1. So therefore, that compound is CaCl2. Ag's +1, NO3 is -1. That's balanced. Calcium nitrate, NO3 is a -1. So I need CaNO3 2. Silver's a +1, chloride's a -1. That is balanced. So now I have balanced each chemical. Next step, I have to balance the equation. Calciums are good. My silvers are good. 2 chlorides to 1 chloride. Neela. Neela, you out there?
I am here.
Okay, I have stop that. I have 2 chlorides on the left, 1 chloride on the right. Balance it.
You would have to put a 2 over in front of the AgCl.
Okay, now I have NO3, 2 of them. I only have 1 on the left.
You'd have to put a 2 in front of the AgNO3.
So guys, this is why balancing chemical equations is so important. Remember, we said that the molar ratios come directly from the coefficients. The coefficients come directly from balancing the chemical equations. So I have a balanced chemical equation. Now I have 2 reactants. First step in my stoichiometry, change my grams to moles. Calcium chloride weighs 110.98. So to figure out how many moles of calcium chloride I have, I take the 5.62 grams, divide it by 110. That gives me 0.0506 moles of calcium chloride. Silver nitrate weighs 169.88. So I have 5.23. I divide that by 169.88. That gives me 0.0308 moles of silver nitrate.
So
What's
we
the-
don't, I'm sorry to cut you off. We
Go
don't
ahead, come
factor
on.
the coefficients in when we're calculating the molecular weight.
No, Curtis,
Okay.
no.
Got it.
The coefficients get taken care of when you're doing the molar ratio. Okay? Now, look at my chemical equation. For every 1 mole of this, there are 2 moles of silver chloride. For every 2 moles of silver nitrate, there are 2 moles of silver chloride. I have my molar ratios. So if I have my molar ratios and I have my moles of calcium chloride and my moles of silver nitrate, I take my moles of calcium chloride, multiply it by 2 over 1. This gives me 0.101 moles of silver chloride I can make from the amount of calcium chloride I had. I do the same thing with my silver nitrate. I end up with 0.0308 moles of silver chloride. All right. Now, at this point, if I want to go ahead and determine how many grams of sodium chloride, can you see I'm just multiplying it by the same number? I would multiply 0.101 by the molecular weight of silver chloride. I would multiply 0.00308 by the molecular weight of silver chloride. After you get through the molar ratio state, compare the amount of moles of the product you've made. Which one is smaller, Mila?
0.0308.
So that came from the limiting reagent. My limiting reagent was silver nitrate. This is the one I'm going to multiply by the molecular weight of silver chloride to get my weight of silver chloride produced.
Okay.
Did you all understand that last step I had?
Can you just go back a slide to like
Yeah.
the fifth step? Because I think I missed
Yeah.
it.
This slide or back one more?
Maybe back one more. Okay.
These are my original weights of my compounds.
Okay.
Again, stoichiometry. First step, I turn my grams into moles of known by dividing by the molecular weights. Okay? The next step I do is I multiply by the molar ratios. Calcium chloride to silver chloride is 1 to 2. Silver nitrate to silver chloride is 2 to 2. So I do my molar ratio of calcium chloride. This means if I had that much calcium chloride, I could make 0.101 moles of silver chloride. But if I had this much silver nitrate, I could only make 0.0308 moles of silver chloride. So this is limiting how much I can make. This is the amount that I report out. Questions, guys? Questions? Did I confuse you?
Can you give me that very last step one more time?
Okay, Hunter, do you understand the molar ratio step?
The 2 to 1.
Okay, look at the coefficients. Calcium chloride has a 1 in front of it. Silver chloride has a 2. Silver nitrate has a 2 in front of it. Silver chloride has a 2. So I took my calcium chloride and multiplied it by its proper molar ratio of 2 to 1 to get the moles of silver chloride I would produce. I took my silver nitrate, multiplied it by its molar ratio, and that's how much silver chloride I would have produced. Remember,
And then you just compare the quantities.
you just compare these quantities. Once you get past the molar ratio stage, you compare the moles. Make sure you don't do it before the molar ratio because you don't know at that point.
Okay, so the chemical that creates the least amount of the product, that's the limiting reagent.
Yes, and that's the amount you report out.
Just like with the bread and ham.
Absolutely.
I have a quick question. By what you report out, are you reporting out the moles or after you change it into grams, or do you report out either?
Jennifer, report out what the question asks for. Generally speaking, report it out in grams. Take it that next extra step and multiply this by the molecular weight.
Okay.
Which is 143.32. This means I can make 4.40 grams of silver chloride.
Will we get the equations on the test, or will it just give us the names of the compounds?
Curtis, it's fair game for me to just give you the names. Since you've been through the chemical reaction, you've been through the nomenclature, you've been through balancing chemicals and equations, it is fair game for me to just give you the name of the chemicals. I won't do the whole thing. If I have like 3 of these questions on the next test, they all won't be. I'll give you one. At the most, I will give you one where I just give you the name of the chemicals, okay?
Gotcha.
Questions, guys? Where are we at in terms of time?
10 more minutes.
36.
Let's go through one more of these, all right? I got 190.1 grams of ammonium chromate and 184.2 grams of copper 2 chloride. What's the limiting reagent? First step, write the reaction. I've got this, I'm mixing these 2 things together, ammonium chromate and copper chloride. Double replacement reaction, I get ammonium chloride and copper chromate. Chromate's a -2, NH4 is a +1. So I'm going to put this in parentheses and put a subscript 2 there. Chlorine's a -1, copper's a +2. There's going to be a subscript 2 there. Copper's +2, chromate's a -2. This is good. Ammonia's a +1, chloride's a -1. That one's good. So after I balance the chemicals, that's what I have. Now, Hunter, I have 2 ammonias over here. 1 over here. What goes in front of the NH4?
CUR.
No, I'm
Or
sorry. I have 2 ammonias here. I only have 1 on the product side. Balance them.
Wait, where's the NH?
NH4. I have
Yeah.
2 of them. It has a subscript 2 on the
Oh.
left side. It does not have a subscript on the right. What goes in front of the NH4Cl?
2.
All right. Coppers are balanced. I have 1 chromate, and I have 2 Cls. Since there's a 2 in front of there, I have 2 Cls. So that is my balanced chemical reactant.
Yep.
All right, guys. Do I have an amount of each one of my reactants?
Yes.
That means I have a limiting reagent problem. I got to find out how much of the product ammonium chromate will make. I got to find out how much of the product the copper chloride will make. Once I figure out how much product they will make, I find the one that produced the least. That is my limiting reagent. That's the amount I report out. So I change each one of them into moles. My 190.1 grams of ammonium chromate, divide that by the molecular weight, I got my moles of ammonium chromate. My grams of copper chloride, I divide that by the molecular weight of copper chloride. This is my moles of copper chloride. Now, you may be tempted to look at the 1.37 moles of copper chloride and the 1.25 moles of ammonium chloride and say, oh, there's less ammonium chloride. So therefore, that must be the limiting reagent. Don't do it. Take it through the next step. Take it through the step where you do the molar ratios. So if I use my moles of ammonium chromate, there are 2 moles of ammonium chloride for every 1 mole of ammonium chromate. This means I would make 2.5 moles of ammonium chloride. I do the same thing with my copper chloride. This means I have 2.74 moles of ammonium chloride I could make. Hunter, which number is smaller? 2.50, 2.74.
2.50.
So this means
Ammonium.
that my ammonium, go ahead.
Is the limiting region.
My ammonium chromate is my limiting reagent. That means I'm going to take the 2.5 moles of ammonium chloride and multiply that by the atomic weight of ammonium chloride, which is, God, I got to do that. 14.01, 4.04, and 35.45. 53.50. So I'm going to take my 2.50 moles, multiply that by my molecular weight of ammonium chloride, which is 53.50. And that would give me 133.7 grams. All right, guys. Actually, I thought this was fairly successful tonight. I thought you kind of were with me. Bottom line, when we're doing stoichiometry, plain stoichiometry problems, find what you know. Turn what you know into moles of what you know. Then look at your balanced chemical equation. Take your moles of known, multiply it by the molar ratio, which you determine by the coefficients in the equation.
So the ammonium chromate would be the answer, right? Because it's the lowest.
Yes, correct.
Okay.
That was that. All right, Chase. But what we did was we used this is the moles of ammonium chloride that were made from the ammonium chromate. Okay, Chase?
Yeah, I get you.
So then we just multiplied this by the molecular weight of ammonium chloride to get our weight of ammonium chloride that was produced.
Mm-hmm.
Okay, so steps. Stoichiometry, find the moles of your known. Use the molar ratio to find moles of your unknown. Then use the molecular weight of your unknown to find grams of your unknown. Bottom line, that's all stoichiometry. Limiting reagent. If you are strategy-wise, you got to recognize it. If you are given each amount of your reactant, if both of your reactants have a weight to it, recognize it. It's a limiting reagent problem. You got to solve for how much each one of those reactants will make of your product. Then once you find out how much product's made, compare the two values. The one that makes the least amount came from your limiting reagent. That's the one you report out. I kind of thought you were with me tonight, guys. So fine as kind. Any other questions, ladies and gentlemen?
No, that's it. Thank you, Professor.
Take care.
Hey, I have a quick question. It's off topic.
I'll see you the last.
Have a great day.
No
Thank you.
problem.
All right, Professor,
Just
thank you.
Mila, I will get to you as soon as everybody gets out that wants
Okay.
to be out.
Hey, Professor, just want to make sure I don't get marked absent. I've noticed on my participation grade, it keeps saying I'm absent for some reason.
Gaith, I haven't put in a participation grade.
Oh, I don't know if it was for lab or chem, but it looked like, I don't know. But yeah, I'm here.
All right. Gaith, is there some
Yes.
reason you keep on coming late though?
Yeah, because I got off of work late.
All right.
Yeah.
No problem. No problem. I'm marking you here.
Thank you.
Thank you, Professor. Bye.
Bye. Okay, Mila, what's on your mind?
Do you know anything about ecology, like the ecosystem and stuff?
If we keep on going the way of Trump, we're going to die.
Well, because this is off topic, but I feel like you might be able to help me out with this. On my property, we have a half-acre size pond, and it's full of tilapia. There's no other fish in there. There's some turtles, but the pond is like really evaporating a lot, and it has not come up since. So we're hoping that it will come up, but the fish are just so like overpopulating it that it's like it's killing off my ducks because it's just so. Like my dog goes in there and she's like pulling out fish left and right. She's just like bored and catching them. So they're just like really overpopulating, and I'm not sure what I should do about it. Like, should I throw bass in there to eat the fish, but then I don't want the bass to start over multiplying? Like, we're thinking we should just try to get the fish out, let it dry up, and try to start over with it. Because we bought the house a year ago, like the property with the house, and they had it on there set up that way, and that's just like the way we had it since.
Mila, it may not have, I don't understand. I would think the more fish that are in there, the more stuff that's in there, that would raise the level of the water.
Oh, it's dropping to the point that like I'll cast net it with the boys to let them like throw the fish back in. No matter where I'm at, if we take the little boat out and cast net off the boat, I'm pulling out like 20 fish a cast net.
Mila, I don't think it's the fish.
You don't think so?
No, I think that somehow something's draining this is Florida. Who knows what subterranean things are going on there?
Yeah,
I don't think it's the fish.
We have 3 wells on we have 4.5 acres. We got 3 wells on our property.
The danger you have is the fact that the lower the water level goes, the more salient, the more salty the water becomes.
Yeah.
That's the great problem with the Aral Sea in Russia. Russia has destroyed an entire lake by continuing to take water out of it.
And like we have a well that is strictly for pumping into that pond, like to the fountain into it, and it's like not even denting it. So I'm not sure.
This is something that you're going to have to call some sort of a water specialist, Mila.
A pond person.
Yeah, they're out there.
Yeah.
I'm sorry. Hold on, Mila. Alec, Rosina, or Omar, do you have any questions?
I just wanted to make sure that
I'm
this
good.
PowerPoint was going to be there in the course content area.
Yes, it will. Well, it's not in the course content. The PowerPoint, it's not there? The PowerPoint should be there, Rosina.
Should be there, right? Okay, I haven't
Yes.
checked, but I just wanted to make sure.
It's what I did, Rosina, before the start of the semester, I went and made sure that all the PowerPoints were in there.
Okay, great.
If it's
Thank
not
you.
in there, email me and I'll get it in there, okay?
Okay, I appreciate it. Thank you.
Because this is a step-by-step process. Omar, have you buggered out on me? Omar's buggered out on me. What he does is he signs up and he assumes that since I can still see his picture there, that I must put him as being present.
I'm sorry. I know that was really off topic, but I was like, who is someone that I would know that would have any bit of information on this potentially?
I mean, I can't really help you.
Yeah.
Mila, that's the only thing I can think of is it's an engineering.
Okay.
It's an engineering problem.
Okay.
Somehow you're getting the water leached from your pond.
That's what because we're like, there's no way, like within a year, it's dropped like 10, like a foot and a half, and it's not come up since.
We're also, if you notice, we haven't had a whole lot of rain lately.
Not any rain at all.
And that when did you buy the house?
In April of last year. And like
this may be just a phenomena of the fact that when we do get into the rainy season, it will replenish.
That's what we're hoping for. Cause like where it was at when we moved in to now, it's not ever been close to it.
Yeah, that's the only thing I can say, Mila.
Yeah. All right. Well, thank you.
Probably nothing more than the same common sense thing that you're thinking yourself.
Yeah. All right. Well, have a nice night.
You take care. See you on
Thursday.
Thursday.